Okay, so this is lecture 13 on least squares. Okay, so least squares problems are problems that are closely related to the projections we studied earlier. Okay, and in fact, we've already done a lot of the hard work in solving least squares problems when we solve for projections. Okay, and least squares problems are problems that arise in many applications. Okay, so here's a question. Okay, so let's say we're given 3 data points. Okay, 0, 6, 1, 0, and 2, 0. And our task is to find the line passing through these points. Okay, so this is the form of a line, as we'll take it. Y equals mx plus k. So m is the slope, k is the intercept. Okay, and we're going to interpret these data points as being in the x coordinate and then in the y coordinate. Okay, so we're going to want our line to contain all 3 points. Okay, so this leads to 3 equations. Okay, so we're going to plug in each of our data points, x, y, into this equation for our line, and then we'll get 3 equations that we need to deal with. Okay? So we plug in x equals 0, y equals 6 into here. We get this equation. Okay, I've put the y on the other side. Okay, and we get 2 more equations for the other 2 points. Okay, now this is looking like something linear algebra can solve now, right? This is the same as the matrix equation ax equals b over here, right? Our coefficient matrix will be this. Our variable vector, x. So this x vector is not the same as the x here. So to distinguish, I write x vector. Okay, so this is our unknowns, a k and an m. And on the other side is our b. Okay, and if you just multiply this out, you'll see that these two are the same thing, the same sets of equations. Okay, so we know how to solve this, right? We form the augmented matrix and we row reduce. Okay, so form the augmented matrix here, right? And I try to put it into reduced echelon form, but after a few steps I notice I get this in the bottom row, 0, 0, 6. Right? Whenever I get something like that when row reducing, that means the system has no solutions, right? 0, 0, and then non-zero means no solutions to the system. Okay, so this shouldn't come as a surprise, okay? If we graph the points, right, here's our point, there, 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 it's pretty clear that no line is going to pass through all 3 of these, right? So we shouldn't expect a solution to this, right? And from the beginning, we shouldn't have expected a solution, okay? So notice if we have an m by n matrix A, okay, when m is greater than n, there's usually no solutions, okay? M greater than n means there's more equations than variables, okay? So why is there usually no solutions, okay? So this is our A here, right? And we have more rows than columns, right? So for there to be a solution to this, what we're asking for is for B to be inside the column space of the columns, okay? So here we'll have a plane, right? A 2-dimensional plane in R3. That will be our column space, okay? And so if you think about it, think of a plane passing through the origin in R3, right? If I pick a random B in R3, it's almost certainly not going to be in that plane if you pick it randomly. Right? That plane occupies a very small portion of all of R3. Right? So in general, when we have more rows than columns, we shouldn't expect a solution. Right? It's going to be very rare that we actually get a solution in that situation. Right? So, next question is, if ax equals b has no solutions, okay, what is the x that is closest? Okay, so now you can see how this is related to the projection problem, right? So if we think about b, okay, remember that every b in Rm splits relative to W, the column space of A, right? We can break it up uniquely like this, right? Into the projection of B onto W and the projection of B onto the orthogonal complement of W. Okay, and we call this part the error, right? Because that's how far we're off from the plane or the column space. Okay, and our work with projections, right? We figured out how to solve for the P here. So the part in the column space closest to B. Okay. This question here is related but slightly different, right? We're not looking for the P, okay? We're looking for the C in this case. We're looking for the C that will be the weights that will give us the P. Okay, so it's a different question, right? The C is going to be in Rn, right? While the P is in Rm. So they're in different spaces. Okay, but from our work with projections, we know how to find this C. Okay, when we solve P equals AC, right? We're actually minimizing the error. We're making the error as small as it can be. Okay, so yeah, when we find the projection, which is the P closest to B, we're simultaneously solving for the X in Rn that satisfies AX equals B. Okay, and remember we called that X the C vector. Okay, and we worked out or we mentioned what the formula was for that C vector. Okay, and it was this. Okay, so let's revisit our example with the 3 data points. So we know there's no line that goes through all 3 points, right? It's impossible. Okay. So our more refined question is find the line closest to the points. Okay, and now we know how to solve for that, right? Okay, so again we have AX equals B, right? And we're looking for the X, in other words, the K and the M, that's going to be the best fit for this, right? So the closest X will be, as we said, our C, which we worked out before, has this formula. Okay, so we have A, we know A transpose, we can work this out. Okay, so just multiply this, compute the inverse, multiply it all out, and here's our C. Okay, so we've solved for this problem. Okay, so K is equal to 5, M is equal to -3, right? That means our line is this. And if we graph it, it looks like this. Okay? So this is the line that is simultaneously closest to all of the points. So previously, when we were working with an equation that looks like this, when solving for the projection, we noted that if we orthogonalize and orthonormalize the columns of A, that greatly simplified a computation like this. Okay? So you might ask, instead of doing this, could I have orthonormalized the columns of A, and that would simplify this computation? So the answer to that is no. Okay, so here's a question again. Okay, could we orthonormalize the columns of A to simplify the computation of C, as we did when computing projections? Okay, the answer is no. Okay, so the reason why is when we orthonormalize the columns of A, that doesn't change the column space. So the column space stays the same when we do that. Okay, it does change the row space, however. Okay? And when we're focused on solving for C, okay, that's in Rn, okay, and so it's in the column space, but if we change the columns of A, then the row space is ruined. Okay, it's not the same. Okay? So you have to be careful when thinking about which vector we're solving for. Okay? Before, we were solving for the projection P, which was in the column space. Okay? So orthonormalizing the columns of A, that's fine. It doesn't change the column space. Okay? So that's why it was okay before, but here we can't do that. Okay, so now I'll define what a least squares solution is. Okay, so if we assume A is an m by n matrix and B is an Rm, then a least squares solution of Ax equals B is a vector C in Rn such that this inequality holds for all x in Rn. Okay, so what this is saying is the difference between A times C and our vector B, our target vector, so the distance between them is less than the distance between B and A times x for any other x. Okay, so this is the closest we're going to get. Okay, and the phrase least squares isn't too descriptive of the situation. It's just referring to the fact that when you take the norm, you're taking the squares of the components. Okay. Okay, so here's a theorem, the pertinent theorem about least square solutions. Okay, so the least square solutions of Ax equals B are the same as the solutions of what's called the normal equations associated to Ax equals B. Okay, so we encountered this equation at a midpoint in our workings on projections. Okay, and this has a special name. It's called the normal equations. Okay, and so how you might want to think about it is, okay, if Ax equals B is not solvable, then what I'm going to do is multiply both sides of this equation by A transpose. Okay, that's how you get this. Okay, and since A transpose times A is a square matrix, okay, and it's more nicely behaved, okay, this will have a solution. Okay, so those are the normal equations, and the solutions to this are the least squares solutions. Okay, so you can see a proof of why that is in the book. Okay, okay, so given the generalized least squares problem, what are the solutions, or how do I find the least square solutions, and how many of them are there? Okay, so this is a theorem that summarizes this. Okay, so given the situation above, right, if B is in the column space of A, then the least square solution is just the regular solution to AX equals B. Okay, so most of the time when we're thinking about least square solutions, we're thinking about when there is no solution to this. But if it does have a solution, then we just call the regular solution the least square solution. Okay, so that's the uninteresting case. Okay, so the interesting case is when AX equals B doesn't have a solution. Okay, that means that B is not in the column space of A. Okay, and then there's two possibilities to the solution set for the least square solution. Okay, so one possibility is that the columns of A are independent. Okay, and that means that A transpose A is invertible. That's a fact we mentioned previously. Okay, this means we get a unique solution. Okay, a unique least square solution. Okay, and it has this formula, right? The formula we worked out when computing the projection. Okay, and if you happen to have worked out the QR factorization, the QR factorization is also well set to solve this. Well set to solve the normal equations. And with a little bit of work, you can show that the least square solution is equal to this. Okay, so remember the R was invertible. Okay, and so the second possibility is the columns are not independent, right? They're dependent. Okay, and in that case, there are infinitely many least squares solutions. So infinitely many C's here. Okay, so in that case, we have to solve it by forming the augmented matrix. Okay, remember the right-hand side is just a vector. Okay? This A transpose A is a matrix. Okay, so what do we do to solve this? Right, we form the augmented matrix and then row reduce. Okay, since it's dependent, we'll get a variable column with no pivot in it, leading to infinitely many solutions. Okay, so remember when the columns of A are dependent, that means A transpose A is not invertible, and so you'll get infinitely many solutions to this. Okay, so that's least squares problems. Okay, as I mentioned before, this type of problem is broadly applicable. Okay, if you've taken statistics, then you know that what we were doing here, finding the line of best fit, is a form of regression, right? It's called linear regression in statistics. Okay, and you don't have to just fit a line, right? You could fit a parabola or any degree polynomial to your set of data.